Hey friends, and welcome back to NTRAS. This is going to be a reproduction of the Introduction to IPv4, the addressing and subnetting portion. One of the big reasons we have IPv4 and IPv6 in our Cisco training and training in general is because IP addressing is really used for all things IT these days. Cisco for networking, Microsoft for servers, Linux for servers, various firewalls and whatnot. So it is really the prerequisite to understand IP addressing before you can really get into a lot of this other stuff, because everything is built on top of IP addressing. And in this case, we're going to talk about the need for IP addressing, including subnetting, CIDR notations, bit counts, the difference between a network and a host, and of course you have to know basic math for IPv4 to really have a good understanding of it. So we'll dive in here really quick. This video will be listed here as soon as I get it uploaded. So you'll see here you can click to watch the video on the page, and I also have it hosted at YouTube so you can watch it and subscribe there. But getting started here, one of the things we have to be aware of is that IPv4 is a 32-bit quad-octal representational numbering system. Pardon my dog. This is a representational numbering system that allows you to address computer systems. Much like your home address, it gives you the ability to segment geographic locations by departments, security boundaries, or just to keep certain devices that are so-called chatty, such as computers, off of a phone network, because you want to have as little contention as possible on a phone, VoIP, or video style network. So jumping in here, we're going to have an example of CIDR notation and subnet. So you'll see here we have the 192.168.0.0 with a /24-bit mask. So you'll see here this is our network, and this is our host portion. The CIDR notation of 24 equates to 255.255.255.0. As we said before, it's an octal representation, so every octal or octet is 8 bits. That's how we can get up to a 32-bit numbering system. Each octet, of course, has a possible numbering using 2 to the 8th power, or giving us 256 possibilities. As you see here, 0 through 255, 0 through 255, 0 through 255, and 0 through 255. This counts, of course, for both IPv4 addressing and subnet masks. So one of the things you'll see here, both of these labels describe the network. In this case, we have 4 8-bit decimal notations. Keep in mind that a bit is a representation of binary or ones and zeros. This means for every bit or character you have 2 possible values. Just like in decimal, you have a potential of 10 possible values. So you have 0 and 1 versus 0 through 9. And you'll see here, kind of like how we have on the decimal system with 1, 10, 100, 1000, 10,000, 100,000, etc. We do the same thing with binary. We start out here with 0. We increment to 1, 2, 4, 8, 16, 32, 64, and 128. So you'll see here that all 8 bits are from 0 to 128 individually, and then we can add them all up to count to 255. So here, 0 is of course 0. You add them up and we get that 255 we just mentioned. But for now, let's take an example from what we have here at the top, 192.168.0.0. This would equate to the following in binary: 11 with 6 zeros. The 11 is the 128 and the 64 equaling 192. For 168 you have 10101 and then 3 zeros. Adding this up, you'll see that we have 128 plus 32 plus 8, and this equates to 168. And then of course we have 0 and 0. So that's kind of the basis to the binary notation we have to start looking at, in that we can take a decimal number and convert it to binary, because that's how computers speak, basically. Everything has to be converted down to ones and zeros. So let's move down here a little bit, and I'm going to show you this table in a different light. So when looking at the bits in a different manner, you'll see here from 128 down to 0, and then the addition of all of them. This will come in handy when we talk about subnetting. One of the things you'll have to be aware of is that in subnetting, we're going to match the bits. So you see here when we add up the bits, 128, 192, 224, 240, 248, 252, 254, and 255. Now keep in mind, this is something you'll need to know much more about in the subnetting section when we get to that. I bring this up now so you can get an understanding of how you can count with binary and how we can count for subnet masks in binary. Now to get more into the definition of binary, we see that it is a base 2, much like how decimal is the base 10 notation. You can really have any combination of bits to create an IP address between 0 and 255. However, you must be aware of the essential IP addressing schemes brought to us in RFC 1918. This link will take you to the ITF website so you can read about that. However, what we do need to know about is the classes of networking: A, B, C, D, and E. Now we'll get into D and E in a few minutes, because we're more so worried about the internal network usage rather than multicast and experimental. So this is a big one to memorize. If you're ever talking with any network engineer, these 3 classes will most likely be what they test you on. So keep in mind that class A is the 10 network, starting at 10.0.0.0 and ending at 10.255.255.255. This tells us that we have a /8 mask, or 255.0.0.0, and gives us those 24 bits, allowing us our network portion and our host portion and various subnets we can use. Keep in mind, with a class A, we have the 24-bit block of potential subnets versus hosts. For class B, we have 172.16.0.0 through 172.31.255.255. This gives us a /12, or the 172.16.0.0 with a mask of 255.240.0.0. Now, when we start looking back up here at our table, you're going to notice we have a /12, or 240. So you're going to notice here we have 4 bits in use to get to 16, which kind of works for us because 16 through 31 gives us a potential of 16 possibilities. This is what we call a 20-bit block, which allows us to create subnets and hosts based on those 20 bits. Now for class C, we have 192.168.0.0 through 192.168.255.255. In this particular subnet, we have a /16, which gives us a 16-bit block. You'll notice that the /16 gives us this network to start out, 192.168, and gives us the other 16-bit blocks for our subnets and hosts. Keep in mind that these are semi-required internal address ranges for unicast. When one device talks to another device, it's on a per-flow basis, which means each communication using unicast will have a flow for each destination device, or basically communication itself. Now when we get into class D, we're going to talk a little bit more about multicast. So if we have a little representation here, I'll bring up my whiteboard. So for unicast, you have 2 hosts that want to communicate between one another, and that communication is pretty much direct. You use the destination MAC address and the destination IP address to be able to communicate with this receiver. Now keep in mind you are connecting to a single MAC address, so it's really the only device that will see it on the network. However, when we get into multicast, this is where we have a multitude of devices that may need to talk between one another. So say you wanted to send a single flow from X to all of these Y devices or receivers. Instead of sending a single flow to each device, so you'd have to send the traffic 5 times. This creates a lot of congestion and a lot of overhead on a network when you're sending the same exact data. So what we can do here is we can specify a multicast address which sends it out once and is received by all receivers, all those that join the multicast group. Now this multicast group is in the 224.0.0.0 network range. So even though we might have our internal address space, say of 192.168.0.1, they'll communicate unicast. Using this range and joining the group will tell the network, hey, if you have a flow to this multicast group, I want to hear it. Broadcast kind of works the same way in that a single device floods or broadcasts out to all other devices on that particular network. There is no real way of blocking the broadcast from being sent to all devices, hence why we use multicast to fix that issue. Only those devices that want to see it will see it. And as you can see here, 224.0.0.0 through 239.255.255.255, and this should actually be a /4, because that 4 will get you the 240. Now if you want to realize how we got this 240, you can say 128 plus 64 plus 32 plus 16. This gets us our 4 borrowed bits, or 240. 1, 2, 3, 4. Like I said, this is reserved for multicast address space only, and you wouldn't use this for any device addressing or unicast communication. Now, as I said before, the multicast groups give a server the ability to send a single flow onto the network for all of the devices that register or subscribe to that multicast address who want to receive the flow. This is mostly used, of course, in video streams, like if you turn your television to channel 3, you get that specific channel 3 broadcast, which is accessible via all televisions tuned to channel 3, but that flow is only sent out once, and those that don't want to see that flow don't accept it. With unicast, each subscriber will receive a separate flow that can cause, network saturation. And lastly, we have Class E, which is 240.0.0.0 through 255.255.255.255. This is also and should be a /4 CIDR notation. Class E is used for experimentation and broadcast. So you'll probably never really ever use the 240 Class E network, but you still need to know it exists. So that will include our IPv4 addressing, getting an understanding of the various classes A, B, C, D, and E. Now keep in mind, once again, you really should understand and memorize the A, B, and C classes, because when they ask you, okay, what are the internal address ranges that you can route with? Not over the internet. You'll want to tell them the 10 network with a /8, 172.16 with a /12, or the 192.168 with a /16. Keep in mind, they may try to trick you up asking you what is the Class B address, 172.16 through 172.31, and that is because we use the /12 network of 240, which if you do 256 minus 240, this gives you every 16 is a new network.